Hello.
Hello.
Hi. Hello, Trevor.
Morning. How are you?
All right.
Glad to hear it.
Great. Well, welcome. So, yeah, let's start out. We have any updates to start out with?
Updates. Mostly, um, as I told, I met with Bradley earlier this week. Maybe we can talk about it later. Um, we discussed some things ahead for the semester, which was good to do. Most of my actual work this week, and it's so funny because uh, it's still on the cusp of being like something to show, but it's been so much work. A lot of Joe Pro stuff. I've spent a lot of this week um, working on how to both sort of visualize and like I've been spending time on the website, but it's much more than the website. Um, it's it's uh, it's like conceptualization of what are like these components of like a project or a working group or a how do you identify what a person is doing in these things, um, and how would you display that both on a website but also in general. So just like a lot of, I don't know, administrative work, I guess. um, I spent a lot of time looking at um, what how what is the language that is used by people who are trying to offer interdisciplinary research to people uh, that are um, hosting several projects or coordinating projects, things like that. That's been a lot. Like the majority of my week has been around that. Um, in terms of this, on this front anyway. Uh, but it's been really tough. Like it's been tough because I'm actually quite proud of myself, even though um, I feel like it's just me talking about it. But I'm really proud of myself in the sense of every day I've really put a lot of effort into this, and it's been good, and I feel like I've learned some important things that way. Um, but beyond that, functionally, there's a few other updates in terms of maybe we'll talk more about this later, but kind of in line of thinking about the semester ahead. I've been looking at some of our past sort of Orel's partners in terms of we've had various I don't know, collaborations with like my uh, New Albany, which is the school I attended in the past, and some things that with the school I'm currently with, and some new things that may slowly be in development here and more in the Boston area in general. So it's been a week of mostly just unpleasant, tedious, like semi web development, a lot of project admin, a lot of like research, the deep ugly things about research and organizational like research organ management at an organizational level, um, and some sort of networking and um, meeting, seeing the virtues of doing some things on campus and getting FaceTime with people, which is something I hinted very lightly at stuff about that. in yesterday's meeting, the open source summer cohort meeting. Um, so maybe more on that later too. But just uh, you know, what this week, in another sense, I will conclude by saying this week has been a lesson in just um, to bring things into existence. It requires a very specific uh, intention to do so,
Yeah.
and sometimes you have to engage other people about it.
Oh yeah. Yeah.
It's very cryptic sounding, but like especially in academia or dealing with these like both vague and potentially bureaucratic systems, like, there's just a certain uh, I've actually been thinking about it in terms of sort of like regulation, which is in a different way part of the polyvagal theory stuff that came last month. But also like in just a feedback control sense, like there's a certain regulatory influence you have to just maintain to shift the state of certain things. So
Yeah.
maybe more about that later, but that's my major opening volley of updates for now.
Well, that's good. Yeah, we did have a meeting on Wednesday. We talked about administrative stuff. So yeah, we're looking towards fall and next spring, basically this coming academic year, and trying to build out collaborations, trying to build out relationships with different universities, and other opportunities to do things to move forward our projects. So that's a lot of stuff that we kind of we put on the table, and I said, we're not going to, of course, do all of this in the fall, or maybe even all of this ever, but it's worth putting our cards back out on the table and seeing where we are. So yeah, and then the intentionality part. Yeah, I mean, you really, it's hard, to really kind of manage research in that way because you're always having to. I don't want to say herd cats, but it's really about like helping the process along, and you can't just let the process help itself along. If you know what I mean?
Yeah, that's exactly almost exactly how I described it to uh I'll put it I'll put it this way because someone was doing new things. A new grad student
Yeah.
was dealing with some things, and I explained it to them that way in a sort of mentoring session, I suppose. And it was like, because they were a bit like, oh, geez, I can't. They're sort of, I don't know, bemused is the right word, but it's like, oh, how come it worked when I like approached the the people interfacing part of the problem this way versus that way, or I talked to this person and it unlocked these set of options versus this set of options, and it's
Yeah.
like, yeah, it's it's kind of like herding cats basically, and what we mean by that is like each component doesn't there's a huge amount of like non-uniformity and maybe even some non-linearity, but like at least non-uniformity in like when you move this way, this person or this aspect changes in this particular way. And I think randomness isn't quite a fair word, but there's a quite a peculiar relationship between the different components sometimes. And I was saying to them like, look, especially in like, I don't even, it's not just academia, but it's sort of this academia slash like your particularly research, particularly interdisciplinary research, particularly like startup spaces, or when you're doing something like really novel. um, it, it kind of gets to the point of like uh, having multiple lines of like solutions or lines of influence. There's a specific word for this I'm forgetting, but like when you see different like strategies that will result in the outcome you want, knowing that they're not all going to win, but they can all like you know have an influence.
Yeah.
And just sort of realizing that that's a norm, and a lot of people are conditioned away from like seeing it that way, or thinking, oh well, I don't want to interfere with things, or it's not my place to say this or whatever. It's like, yes, but um, there's an element to just understanding that that's, you know, part of things. So more about that later, perhaps. But I totally uh, am in line with what Bradley was saying.
Yeah. So I mean that's very different than the way we usually fund research. Or I shouldn't say that. I should say the way that the funding agencies fund research. Sometimes they
Hmm.
fund it on promise, but a lot of times it ends up being like, what can you do in this period of time? And if something has long-term promise, then maybe it gets funded. It probably doesn't get funded just on that alone. And so, like sometimes, if you're dealing with a startup, that's maybe more of what you're doing is you're funding things for the future, and then of course, the promise, needs to be there later, I guess, or else people pull their funding or you can't raise more funding. But yeah, I mean, having that decision making, where you're not saying I'm going to pick winners, but I'm going to pick influential projects where sometimes I'll spend 6 months to a year on something and it'll be an influence on something else, or it'll be something that will build to something else. You might not produce a concrete tool or a concrete outcome, but it does contribute to that other thing. So that's kind of what you're referring to, and I think a lot of like research that's important. It's an important component of it. And that's not the way we think typically in thinking about managing projects or funding projects.
And I think it's even like, not to turn this into too big of a rap session about it, but I think um, it's really, uh, at least what I've learned, or what I've come to realize in my um, growing experience, I guess, is it's very like code switching. It's very to go between the different environments. And like if you're trying to get a specific grant, you have to present present ideas in a very specific way. Like that's kind of been indirectly reinforced by everything I've been looking at. Like when you're when you're thinking about how do you talk about the work you're doing in a way that's public facing, grants like related to a grant, or getting like things from either like a media attention standpoint or just an accessible standpoint for the people that the organizations that are going to look at it and say, okay, here's how are you talking about this in a way that fits, whether it's like someone investing in stuff, demo or die things, or like a federal grant. And they're all kind of uh, it's different, and knowing the different ways of communicating, it's almost like meta. It's not just science communication, or top, like one of my early PIs, which I admire for how she introduced this, because I can't remember how she did, but it was a really good way of doing it. But basically, in the context of being a researcher, it was like going all the way down from like way deep down into what individual components of, in this case, like the brain or the biology is doing, up to higher level to like systems, and then moving from actual physical things to theory, and then theory to like projects, and projects to like, like what's this paper is deliverable in the lab at the time. Like that was cool, but it's almost like that plus this other level of now realizing how you how you communicate that and even talk about that to like a prospective lab mate or a funding person or in the startup space or another spaces. It's all different, and it's all like you can't if you are talking about it in a certain way, to certain like audience and people with different intentions, uh it won't necessarily hit unless you're doing it the right way. You have to sort of code switch. You have to be aware of that. This is like super, you know, higher level administrative and like almost like research strategy, which is sort of, I don't know if that's a real field, but I feel like that's a thing, like strategic initiatives of research and innovation. Uh, I don't know if that's a thing, but it feels like that's something that I'm constantly put in the position of having to deal with and think about because it just, I don't know. This is probably why I bring it up here so much is like, I don't know where else to talk about it as well. So,
I see Lucas is here.
yes.
Maybe he can give an update in a minute on what he's doing, but I wanted to talk about a few things before then. So let me share my screen. So I mentioned that we did administrative meeting on Wednesday, and I mentioned about these project cards that we've had in the past, where I tried to summarize some of the initiatives in the lab and put them on these cards where people could read them over. And it was more of a social media device where we put them out on social media. People could read them and get more information about the projects. And I was looking back at them and I was like, well, this was definitely a first attempt at this. So let me pull this up. So this is, okay, so these are the project cards. Some of these are empty because we never really filled them out. So there are themes like developmental AI, and I think we've talked about this. I think we did these project cards in like 2021, maybe updated them in 2022. So they have a little bit of time on them. And so developmental AI is something we, at the time, were working towards as a project. And I think since then we've decided that that's more of kind of a in-house theme that we're kind of building from. So, maybe this is an idea, maybe this is a specific project. And I've noticed, like, going through these cards, that we've had this a number of times where we have these, kind of general ideas of things that we're interested in, and trying to make a card out of them may or may not make sense. So, kind of getting the right unit of what the project is that you want to engage people with is the key. So this is one example where you have the education and content streaming stack. This is an idea where we wanted specifically to, and some of these things are pretty dated, where we wanted someone to do things with social media, with education, delivering education through the discussion channels we have, the YouTube channels we have, and things like that, putting together sort of this virtual education and content and making it useful to learning and research collaboration. And so, we have this as sort of an idea. Another one is innovation in open science. So, again, like we have all this stuff in open science, and it's kind of like at the point where it isn't really a formal project that we do. So, like if you go to the website for the lab, you have some of these formal projects, but you also have these kinds of things that are not really formal projects. They just kind of exist on their own that we talk about a lot and we've done some things on, but not really built a project around. And one of the points of these posters or cards is that it gives people an idea of a unit that they can grab hold of and start working on for themselves. So that's why we're doing this. And again, these cards are, pretty dated, but they have ideas in them. This is one that Jesse had here: technology, society, ethics, law, and philosophy. And we have some of this. Yeah, well, it takes you back, doesn't it?
That's so old school.
It takes you back, yeah.
Like origins of society, ethics, tech, which is actually a thing now, and like a banner that did things. So
Yeah. So some of these we've actually worked out more. So like this is like this chunk is now kind of society, ethics, tech, and then within that we have chunks that someone could grab hold of. So in other words, we could take this card and revise it to say this is part of society, ethics, tech, and repurpose some of this text, The deliverables, I think, are pretty much, you know, we just, I don't know, we maybe need to update this for things that, for more specific types of chunks that we want people to grab hold of. So, within society ethics tech, there may be some issues around just philosophy or just ethics. So, we have a call for that. And then the deliverables are more specific. This is just kind of boilerplate. So this actually, I think we can update these, but we have to think about kind of what we want out of them. So yeah, this is reconstructing cybernetics, which never really got off the ground. I mean, we never found anyone who wanted to do this stuff, but we did do something. We have done some things with papers and with some meetings and meeting series and things like that where we've driven this forward. So now we have to go revise this card according to that. But really, this just kind of describes the kinds of things you could do with reconstructing cybernetics. So, I mean, I'm not sure what level of specificity to make this. I'm just kind of thinking about how to repurpose these cards in a way that makes sense. And then developmental Brainberg vehicles. This is something that's a very, has a very specific set of deliverables. You can work. We have for this initiative, of course, we worked on these developmental Brainberg vehicles. We have a paper on this. We used to have a working group on this. We have open source repositories. So we have very specific things that you can engage with. So this is much, much more specific than something like reconstructing cybernetics, which has a lot of opportunities to sort of forge your own path, conceptually speaking, but is still, something that needs to be updated and is more specific than this at this point. So, yeah, I wanted to pull those up. I've been meaning to do that for a while. But the idea there is that, we have this set of tools that we, maybe guidelines for participation. We want to link back to the projects. We want to refine those with respect to the projects, and maybe it'll help us refine the projects more in the process.
Yes. I don't know that I want to say this is what can happen based on what I've been doing this week, but I'm at least looking into sort of formalization of some of the nature of developing a project, and I've spent a lot of time this week kind of comparing different ways, and it's different because of to kind of go back to what brother said earlier, it is different when a lot of generic, I don't want to say generic, but I'll say generic here, sure. Generic funding and project development is oftentimes of a different nature. So when you're dealing with an interdisciplinary or nebulous space, or doing things in a way that just hasn't really been done at a conceptualization or development of idea level, it's just a different, rather than, okay, here's an established, here's an established train of thought with a very obvious, journal and very obvious funding path and a very an established discipline, and here's sort of the beaten path of that. It's just a different kind of thing. So having the discussion and having the opportunity for people to see what's going on and then formulate, staging the development of the idea and the research project itself is its own path. So yeah, I guess what I'm saying outside of my weird meta talk here is, let's look at the cards, and I don't know if it's going to be one of those things where previously, for a concrete example, previously with the University of Albany, we've had to submit we've had to present ourselves as, oh, we are an organization someone can come along and do undergraduate research experience with or get experiential learning with. Here's what we offer in terms of this and that. So a lot of those posts or submissions or like postings of what happens are like, I'm a cognitive science research lab, or I'm a neuroscience lab, or or I'm from the, different labs and organizations across the campus. So what we've done in that case is present not necessarily these cards, but sort of something that's broad in a broad enough space to say, here's some topics we're covering, and here's what a potential you can do there. That's University of Albany, and it's that's sort of one way in a situation where you're kind of constrained about what you can convey. But where I'm going with this is that I think reviewing the cards is a good step for us to get to. We can do specific solicitations for. Let's have an intern on model building. Let's have an intern on reconstructing cybernetics or whatever. We don't have to make all of these things, and it's sort of this mix between. You can kind of just make a whole bunch of open internship specifications if you want to. We've done that in the past, and they exist in different places. But if you really particularly want, if we want to promote something specifically as an intention for the fall semester, we can make that choice and like try be a little bit more intentional about making an a solicitation or a call for involvement or a call for whatever about that topic. Like, I envision myself doing that for like Cognition Futures, maybe even specific society ethics tech, because there's a few things in it. Like I'm interested in some of the data science work I've been doing in my actual grad program. There's a few outlets of things I want to do there, and they have the most immediate home for them would be society ethics tech, because it'd be like data ethics is right there in the middle of all of those things. So I mean, I envision making something around that, but I'm also as putting my lab manager hat on specifically. If we want to do other things that way, I'm happy to like work to build out. Okay, we've kind of talked about brain organoids a lot. Are we at a place where we could mention that? Or we talked about we're kind of doing things with the cybernetics reading group, but it's not quite reconstructing cybernetics, but maybe it is. And there's the model building stuff, and I know Bradley's. I don't know if you're going to talk about that later, but you're doing specific things in that space. We have these Google Summer of Code things that are going on, and we have a history, or at least a potential things that have happened in the past, is where someone stays on with that through fall and builds it out, either with us or excuse me, sometimes getting different learning, different ways that helps them out through their school as well. So like with the academic credit or not, like those are different pathways to go with those sorts of things. So finding out, conveying all this and putting these options on the table are things we can do between now and the next month or so, I think.
Yeah, look forward to it. So yeah, this week we did a number of meetings. We had the OpenWorm meeting, so that was actually an update that I gave, and that was on a number of different papers that I wanted to cover and discussing the kind of things in that space. So check that out on the OpenWorm YouTube channel. Then we had an administrative meeting on Wednesday, which was, of course, Jesse and myself, and we talked about this sort of thing in more detail. So, and then yesterday we had our open source meeting. So it was Jesse and Morgan and our GSOC students, and we talked a lot about sort of different progress and different projects. So we have our open source sustainability project. We have 2 people working on that. And the Graph Neural Networks project, which, of course, we had an update on that. And then we talked a little bit at the end about some initiatives that Morgan is involved with NeuroFedora and things like that. And so that was our meetings for this week. Jesse said also to talk about later, Morgan might be coming to Boston, or going to see Jesse in Boston maybe, or just going to Boston. There's
I think Morgan's coming here for much other reasons than to see me, but yes, of course, okay. To see me ultimately. No, but I think there's some there's a conference
Yeah, the
that some of the events
computational cognitive neuroscience conference at MIT, which is
yes,
happening, and that's why he's going to Boston. But yeah,
and some other things. But yeah, if it happens, that's cool.
yeah,
I
yeah.
don't mean to interrupt what you're saying.
Unsure if I can go to the event, but definitely trying to cross paths or generically being in Cambridge, Boston, around MIT. Yeah, that's always good to have. Like, you go somewhere and you get in, you take it, soak in the environment there. And yeah. Okay. So I don't know. Lucas, hello. How are you?
Hi, how are you guys doing?
All right.
So I'm just here to, I think Bradley, I asked the question from Bradley, and then he asked me to join the meeting today just to talk about something.
Yeah.
But yeah, to give you guys an update, I'm currently working on the coding part of the project. So just to give for the people who don't know, I'm working on my studentship, OpenWorm Studentship, and the project that I decided to do is kind of related to our recently published paper in BioSystems. So what I did in that project, which is related to the genomics of C. elegans, was to do a bunch of data collection and some parts of protein analyses. So I could just send the link of the project here just to show you guys.
Okay.
Yeah. Um, yeah, so it's here. So if you guys go to the so
That's a link to the paper, basically.
yeah, that's linked to the paper,
Okay.
which yeah, it's mostly so what I mostly did was protein count. So I used the blast URL to blast tool on NIH to do the protein counts. So my OpenWorm project is just trying to use the API of the blast API to turn the results that you get from blast to a JSON format, which is the easy part. However, the harder part of the coding project is to so because I did all of the protein counts manually, so now I'm trying to find out. Okay, I get the results in the JSON format. How, like, hypothetically, I could just like I don't know how I have to kind of turn that from a manual thing to an automatic thing, because what I used to do was that okay, I get the results from the blast search, and then I look at the proteins because sometimes there might be duplications, sometimes blast gives you a name, like it might be another name for the same protein. So yeah, that counting part might also be done manually. I don't think if there's a way to do it using coding and stuff like that. So yeah, my question today from Bradley was to ask him how the second part of the project works, because like the second part of the project is to use the protein counts, or like the protein counts to so we use this data to model the embryo of C. elegans, which I don't really have a lot of. I haven't done a lot of training, or like I haven't been doing a lot of modeling. So I was wondering how we use the protein count results to model the embryo of C. elegans. So yeah, that was my question, and then
Okay.
after that, I could just put this all together and like publish it on the repository and do finish my Jupyter notebook that I started.
Okay. Well, I think in the second part of the project, the idea is to take the protein data, of course, to sort of get that analysis in a higher, like kind of the form that we did for the paper. We did the queries, put together a data table to automate that process, so we can, at least to some extent, so we can get, we can go maybe find other proteins or whatever. And I think we talked about adding proteins to the list and getting that pipeline worked out. So the studentship, it doesn't need to be a huge amount of work. It just needs to be usually focused on bioinformatics and getting those tools worked out. And then, that allows other people to pick it up and use it for other reasons. Now, the second part, this is going to be where in OpenWorm, one of the things we do is we take data from different sources. It's usually something like, a primary paper, or it could be like a genomic, like NCBI, a genomic database, where you have access through APIs or through different interfaces, different file types, to put together data sets that are annotated, that have some provenance in the genome or in protein space, and then put those together to do what you want to do. So with what you have now is this group of proteins. You have some information about them. I don't know if you have, I guess you can go get the sequences if you want. I don't know if that's something that is useful for what we're doing, but we at least have the IDs and we have that pipeline worked out. So once we have that, then we can attach the proteomic data to models of the embryo. So I guess what I'm saying for the second part is we're not really directly modeling the embryo with proteins. We're trying to attach the proteomic data to things in the embryo model. And the embryo model being these other data that are put together. And so we can attach the protein data to that model in different ways. So what we have for an embryo model is basically, cell information, so cell location information, cell time information, so how long is a cell alive, and so different developmental cells will, divide from their precursors, and then they'll divide again, and those cells are around for a certain amount of time. So we have those cells, we have their position, we have information about different regions of the embryo, so the different movements of the embryo and how the cells sort of migrate during that process. So we have all this information about development. We also have information about larval worms. So we have this similar models in larval worms. We have cell information, their position, their timing, the timing of larval periods. We even start to get some data on the neurons at that point and the synapses. So we have a lot of information in that model. Now, none of that, of course, is genomic data. So that's what we're trying to incorporate into the models. And so in your case, you have proteins, you have that pipeline. And there are two things I'd like to do with that. So I'd like to attach the genomic data that we got from the paper. And that was largely something that I did. And that's something that is not as automated. And maybe, we can walk through how maybe to automate some of that. But I don't really want to focus on that too much. But to attach the genomic data that I have, that we can get, and it's largely just creating like a file, downloading a file of the data, doing some search operations within that data, getting some numbers, and then attaching that to the protein data. And then, attaching that to the embryo. So I'm not really sure how we want to do that yet. So it might be better just to kind of, for the second part, just to attach genomic data to the proteins and then kind of put it in a framework. And I'm not quite sure how to do this yet, so bear with me, to attach it to the embryo models. Because the data isn't for specific cells, And this is something that is kind of an issue with a lot of secondary data sets. We can't really make statements. We can't attach it to single cells, but we can attach it to the embryo itself and a more general aspect of it. So I guess what I'm saying is we need to think about how we might attach the protein data. I'm not sure what that looks like in terms of a deliverable. Definitely like attaching a certain type of genome data and analysis to that, and then attaching that to the embryo models or generally. And then maybe another project would be to kind of look at, maybe we can get data for specific cells. I don't really think we can do proteomics at the single cell level, at least right now, but we definitely have, the data for the entire embryo, so we can make statements about that. But that's where we are with that. So, I guess what I'd like to see from Lukas is I'd like to see the Jupyter notebooks. I don't know if you can send me a link. I don't know if you're working on GitHub, but that would be good to have that up on GitHub. And send me a link to the repository where we have the notebook. I can look through the notebook, look at the work. I can make notes in the notebook on what needs to be improved or what how that's going to fit together with the data that we have.
Okay, yeah, I'll do that after the meeting's done, I guess.
Yeah.
But yeah, makes sense. So yeah, because the first part, like using the blast URL to turn the results to the JSON format, that part is like pretty much the easier part of the coding.
Yeah.
But like the second part is what like really kind of like frustrates me because I can't really figure out a way to do it. And also like the OpenWorm project's like the entire purpose behind doing the project is is like going out there doing a bioinformatics project for and showing others how to do it. So I'm not sure how useful it will be for the other members of the community. That's why yeah, we have this project, but like I want to make it
Right.
most useful for others. So
Right.
yeah, that's what I'm thinking about.
Well, I think the resources that exist in the OpenWorm community are a little bit divorced from what we're doing here. So, like, they don't do a lot of stuff with molecular biology there. They do like cells. We have like ion channels, I think, and some other things. Of course, we're focusing on the neurons a lot. So we have that type of data. But attaching like proteomics data to that is a challenge because it's like, well, we didn't really think about that. So like, and of course the specific proteomics data that you did for the paper wasn't really neuronal, or it wasn't explicitly neuronal. We could do that, but if you have this pipeline down where you can get things from the API, bring them into a set of JSON files, that allows us to go and find proteins that are more neuronal specific. We can find different candidate proteins depending on the question we're asking, and then we can attach it to the model. So, it's not enough just to say, like, I have this list of proteins and that's it. Because we have all sorts of, questions we might ask. And because it's a general model, it's just kind of like, I might be interested in one set of questions, someone else might come and ask another set of questions. Now, the benefit of using JSON files, of course, is that that's what a lot of the other OpenWorm data, that's the format that they use. They use the JSON format. And of course, that allows us to associate metadata with the numeric data. So if we have some numeric data that's useful, we can attach information to the metadata. And the metadata is what we're going to link to the actual model. So if we have like a specific protein name and a specific annotation or function, and some information about the isoforms and other things. And I know you had a methodology for like normalizing that. So that's important because we're kind of we could go down a rabbit hole with proteomics data and linking it to specific things in the worm. But that's where we would make that connection, is in the metadata. Like, yeah.
Okay, yeah, that's great.
Right.
Yeah, so I'll do what you asked me to, and hopefully we can figure something out. Yeah, thanks.
All right, good. Thank you. Thank you for the update. And yeah, again, it's kind of hard for me to meet off hours like that. So I don't know if we have like another time. Well, we can meet sometime. I'm sure we'll find a way. But yeah, the OpenWorm Studentships are great. And it's not meant to be like this exhaustive thing. It's just meant to get people experience in bioinformatics, and it's meant for people to take data that's out there and get it into a format we can use. And that's very valuable because, there's a lot of data we can use that's
So, I mean, I'm seeing this, and I'm just because of everything I've just been doing and talking about. I love to sort of make essentially a project card, as we're saying here, or a project description on things I'm doing for websites of this studentships, because people, I think, have heard about them and I knew about them. I don't think I'm going to be able to pursue one myself or anything like that, but more like I think it's a great opportunity that DevaWorm and OpenWorm has. So I'm both like kind of recording what Lukas is doing in his own project, which is really cool, which is mentioning to other people that that's a thing. I think would be an exciting, we can, I don't know. I mean, I guess I have seen a few things about it in the past, but I'll have to update myself on like how OpenWorm talks about that. And it's great to see Lukas, diving into that here.
Yeah. Well, it's something that's been pretty informal. It's been pretty informal. They kind of like offer them to people who work with the different senior contributors in OpenWorm. So, like we had one year, we had someone who kind of refactored the Blender model of the elegans. So that was just like making the Blender model, bringing it up to speed in terms of the Python. So went from Python 2 to Python 3, making it easier to like download the Blender model and work with it. And that's like, again, it's a project that would not get done unless you offer some money and offer some, some time guidance. Yeah, attach it to something like. But yeah, I mean, it's it's something. It's pretty informal, but that's what happens a lot of times. There are a lot of opportunities people don't know about. That's why we have these cards, because they help people see them. Oh yeah, there's this thing and I didn't know it existed. Or there's this opportunity to collaborate I didn't know existed. So
yeah.
Okay, so thank you for that update, Lukas. And so let me move on. I have some things to talk about here. We have some features, pretty interesting stuff. So the first thing is the general channel. I'll bring your attention to that. We have a couple new people in the general channel. We have Vineet Tiravati, who joined. I think this was on the invite of, I invited him, but it was also Hussein who met him somewhere, and he's doing this stuff with neurotech, and this is something that Morgan is interested in, of course, and I think Vineet is interested in both organoids and sort of neurotech, and so there's a really interesting possibility to make some collaboration happen here. And so I don't know if we want to set up a meeting or what, but we'll figure something out. So that's Vineet, and then there's Ben Huang, who's is an assistant professor of neuroscience at Weill Cornell, and he's doing this really interesting stuff with I guess it's neuroimaging, live neuroimaging, where you have he has a population of mice, and they have these subcortical arrays that they put on the head of the mouse, and they can track neural activity when they're doing continuous behaviors. So when they're navigating a maze or something like that. So he has this whole platform around that, but his interest for this is also theoretical. He wants to develop certain theoretical frameworks he's interested in ecological psychology. He's interested in systems neuroscience, and by that I mean like complex systems, dynamical systems. So he's like, I talked to him through Neuromatch. So did Jesse, and we talked about that
Yes.
a little bit. But yeah, I'd like to meet with him. I'm going to try to meet with him, um, in the future, so we can kind of maybe drive some collaboration forward here. And so yeah, there's a lot of ideas here, but we need to capture them and direct them in a certain way. So I want to just bring those two people to our attention, so that we can get maybe if people are interested in collaborating, that they can meet with them and that sort of thing. So let me go on to some of the other articles that I have here. So I think this was actually from the Slack, or I'm not sure. No, this couldn't have been from the Slack. This was a couple days ago. So this is an article on this. We talked about the ARC project, or the ARC Prize. This is Francois Cholet's ARC Prize, and this title. This is from IEEE Spectrum. New competition seeks to unstall AGI progress. So unstall means that we want to sort of drive it forward because it's stalled, apparently. So this is the idea that our knowledge of machine learning and deep learning and all these methods, where we're increasing our research, or we're increasing our knowledge, but are we getting closer to some sort of artificial general intelligence? And so that's what the ARC Prize is meant to sort of drive progress on. We've talked about the ARC Prize before, but this is this has to do not only with the technology and the methods, but also the notion of intelligence, or artificial general intelligence. So the idea here is to sort of develop benchmarks to sort of figure out how to maybe characterize intelligence better, but also to get closer to some sort of intelligence that we can simulate. So it says the ARC Prize will test AI models' abilities to infer a rule set it's never encountered before, such as filling in only the squares in an image that are fully bounded by green squares. So this is where it's not just about training a model and generalizing that training set, which we've talked about, which is hard on its own, but dealing with things that a system has never seen before. And you wouldn't even call it out of distribution behavior. It's more like out of concept behavior, or out of inconceivable behavior, something like that. And we can do that as humans. We can do that. Other animals do that, of course, as well. But we don't have, we don't see the path towards simulating that. So, artificial intelligence models are constantly contending to crush performance benchmarks. Of course, we have performance benchmarks, but those are kind of, tell us something about how accurate the model is, or how much, loss it can minimize. But these models have been slow to surpass AI IQ tests. And so there's an article here from IEEE Spectrum. How do you test the IQ of AI? And that article is, again, about building these type of AI IQ tests that can probe for concept learning and analogical reasoning. And, there are a couple of examples here of human IQ tests where, can we just apply those, or do we need to come up with our own kind of tests? Now that being said, of course, human IQ tests are flawed in a lot of ways. And so, measuring that is going to be difficult, especially since you have to measure IQ within the context of sort of a population measure, which is, problematic. We've talked about this before. And so this is there's a bit of work that's been submitted in their IPS where they've kind of been working on this theme. So yeah, this is okay. So I have a thing in the chat here. Jesse says, I'd really like to see both of these articles, especially relative to critiques of IQ. We're going to get to that. Yeah. So there are two articles here. So this article, to really judge an AI smarts, give it one of these IQ tests. And this other article on new competition seeks to unstall AGI progress. So there are these, this just kind of talk, they interview Francois Chalet a little bit. Ultimately, the ARC Prize is trying to accelerate AGI research through fresh ideas and innovative open source solutions, as well as speed up the timeline for AGI. So Francois says, right now we're stuck in this large language model only world. So like a lot of what we consider to be like intelligent behaviors, large language models generating text, generating, things that look intelligent. We don't know if it's actually intelligent, but it's, but LLMs are not by themselves intelligent. They're more like a way to store and retrieve knowledge, which is a component of intelligence, but it is not all that there is. So, storing and retrieving knowledge, like memories or, like maps of the environment, those are a component of intelligence, but it's not necessarily all there is to intelligence. So, we have like good models of, so I think memory retrieval and, some good models of representations of the environment. And you can generalize from that, which means you go back to that model and you like basically extract information out of it and you build, some, action in the world. But that's not all there is to intelligence. So really defining this is hard. And this is, trying to carve it at its joints, I guess, is the point. And so getting down to the ARC Prize, it's developing some technique that can be useful there. Julian Togelius, who's at New York University, agrees that there exists a bit of monoculture. We're using the same few architectures all the time. So using the standard architectures, the state-of-the-art architectures, may not actually give us a full view of how to simulate intelligence. We use, like, say, neural networks, and there's certain things you can do well with neural networks, and certain things you can't do well, and so we only really kind of benefit from the things that neural networks do well. And as a result, we kind of focus on those aspects of intelligence. So I think this is, a kind of a nice set of articles. But then there are also some critiques of this. This first article from Noema is "The Danger of Superhuman AI is Not What You Think." So this is by Shannon Valor. This is an essay. The rhetoric over superhuman AI implicitly erases what's most important about being human. And so this is sort of a critique at this idea of superhuman AI. So the idea that, if we can measure intelligence as a certain set of things, or at least we have a concept of intelligence as a certain set of things, if we just simulate that and surpass human performance on those tasks, that we have superhuman intelligence. And so that's I guess one way to do this. But the problem, of course, is that's not really all there is to intelligence. That's not really like, I think a good definition of intelligence where if you exceed a performance benchmark, you have become it's become this superhuman technology. So this kind of draws from a lot of the rhetoric that happens in the field, where people talk about superhuman capabilities of models. And really what they mean is it's like you have a human performance benchmark and you exceed it. And so, maybe there are things that machine learning does a lot better than human learning or biological learning. And it's because machines do those things better. And so, it's kind of we have to think about the definitions of intelligence again and kind of the definitions even of our benchmarks. So it kind of goes through, she talks to Yashko Bengio, who talks about superhuman AI, and she's, kind of finding this to be like kind of a communication barrier because, a lot of people, when they think of superhuman intelligence, maybe don't think of the kinds of things that researchers are thinking about. And so thinking about the dangers of these kind of systems, that leads into that kind of whole discussion as well. And so this kind of goes through the critique. So this is what Jesse, actually, one of the things he was talking about here. So the idea that computers work on the same underlying principles that our brains do is not a new one. Computational theories of mind have been circulating since the 20th century origins of computer science. There are plenty of cognitive scientists, neuroscientists, and philosophers who regard computational theories of mind as a mistaken or incomplete account of how the physical brain works. But it's certainly not a bizarre pseudoscientific view. It's at least conceivable that human brains, at the most basic level, might be best described as doing some kind of biological computation. So, of course, we've talked about this where just because the computer has an analogy with minds or brains, that it may not be doing the same types of things. You might not be able to characterize machine performance as analogous to human intelligence and the performance of such. And, making those kind of analogies has a cost, which is that we misunderstand what the models, what the machines are doing. We misunderstand intelligence and so forth. So yeah, this kind of talks a little bit about this and unpacks it a bit. Now, I would say that there's a lot more discussion here. This is just one view on it. And this is one quote here. Once you have reduced the concept of human intelligence to what the markets will pay for, then suddenly all it takes to build an intelligent machine, even a superhuman one, is to make something that generates economically valuable outputs at the rate and average quality that exceeds your own economic output. Everything else is irrelevant. So this is really kind of going through a lot of kind of
pretty good paragraph.
Yeah, assumptions of why we're trying to build superhuman AI in the first place is because there are these economic imperatives that are driving it.
And it's so wild because I know this is a tangent, but I was at literally at an event earlier this week. It was a clinical AI event, and it was just funny because there was a moment in the talk where I was like, well, why are we doing all this stuff? And the guy was just very transparent, saying well, it's to help people, right? It's like, I mean, we're doing it there's a huge profit incentive to do this, and it was just this sort of. I'm not trying to be sensational about it at all. More a sense of people have to understand at the the people guiding where funding and ideas go are influenced by that, and not in in a nefarious way. It's just that's a factor. I feel like that paragraph encapsulates it really well. And it's just so weird because different the amount of hey, understand this is it's a difference between saying this is a factor and being uneasy about it, or being a factor and treating it like it is a factor versus kind of not really talking about it, but it exists anyway. And I think it's just so interesting to see which part of the discussion, especially about AGI stuff, because a lot of AGI talk tends to go in the direction of very futuristic long-termist stuff, or I mean EA stuff, and I think all the lecture-driven Elon Musk podcast space. And there's sort of varying degrees of how do we talk about that from a sense of what, and that same statement to really I'm gonna give back the mic after this statement, but that paragraph is so nice because it applies across many different fields of study. It's not just the AGI talk. It's that's a major part of the evolution of what we now call mental health spaces, or psychiatry and DSM. That's a factor too. Where did these things come into play, and how are the metrics designed that are there's an interesting relationship between science, empiricism, and what can be measured, and what can be measured, and what can be put into, well, more of this number is better.
Yeah.
So, yeah.
Well, yeah, I mean, and a lot of and we talked about that one paper where they tried to define intelligence based on the literature. Like you go to psychology, you go to clinical studies, you go to, I guess,
And
AI, even where they're all different definitions. And so using a metric across those areas is kind of fraught from the start. So
and that's I have a long-term thing I'm working on is exactly that, in the sense of, in lieu of there being certain, like, I would just, I know some things are just like ancient philosophical questions that don't have answers, but some things aren't that. Some things are just actually immature fields that we haven't developed enough to talk about in ways that are sufficiently useful or articulate. So in lieu of having that, what is a much more tenable way to, reference progress or monitor progress in a space? I think that's a really key concept that has shaped much of, how things are now. But we don't really, how do we talk about that, right? But to be more direct, yeah, like intelligence in and of itself, I think that's something that I think is something, I don't know if it's up to a project card, but it's more like a specific theme that I think is I'm very glad that we talk about here periodically, because it is a factor. Like we're kind of having to it's related to the challenge that I brought up many different times about, like, synthesizing from a conference or a book, like, or even set a discussion, like, okay, we're all talking about this stuff, but we don't really converge in anything, and it kind of just stays in this way. And not in a sense that there has to be convergence or one magical theory for everything, no, but more like understanding where things are in the space of those competing ideas is important. So
yeah, definitely. So that's talking about superhuman AI and some of these benchmarks and getting a sense of what when we say a model is intelligent or it's exhibiting intelligence, or I won't even get into sentience yet because that's like a whole different kettle of fish. But like, what does that mean, and can we compare it with biological intelligence, and how would we do that? And it's turns out it's not anywhere near as easy as people like to claim. So this is an article Melanie Mitchell in Science. This is from 2024, so this is pretty new. This is from March. And this is debates on the nature of artificial general intelligence. This is, I guess, another critique, but it's sort of just kind of characterizing these different debates and sort of what are you dealing with when you have an artificial general intelligence. I mean, is it something that you could compare to human intelligence? Is it just its own thing? Is it even general? And that's another issue that, if you develop a technology, say, to simulate some task, and it does really well in that task, is it general or is it just kind of simulating that task really well? I mean, that's why one reason why we use benchmarks, where you can do many different types of things and see if your model, it does equally as well. And that may be one way to kind of characterize this general aspect of general intelligence. But again, this is not something that it's all very loose and it's all very fluid, and that's not really doesn't necessarily lead to good science. So the term artificial general intelligence has become ubiquitous in current discourse around AI. OpenAI states that it's a mission statement link, is to ensure that artificial general intelligence benefits all of humanity. DeepMind's company Vision, of course, notes that artificial general intelligence has the potential to drive one of the great transformations in history. And so this basically says that, there are all these kind of mentions of artificial intelligence or artificial general intelligence being this benefit, being this, transformational thing. Well, if we can't define it, then, it's not, I don't know if that's what it is. So one could not be blamed for assuming that the meaning of the term AGI, or artificial general intelligence, is established and agreed upon. However, the opposite is true. What AGI means, or whether it means anything coherent at all, is hotly debated in the AI community. and the meaning and likely consequences of AGI have become more than just an academic dispute. Of course, the world's biggest tech companies are making decisions based on this. But a deep dive into speculations about AGI reveals that many AI practitioners have starkly different views on the nature of intelligence than do those who study human and animal cognition. Differences that matter for understanding the present and predicting the likely future. So this goes back, to this idea of early AI. So the original goal of the AI field was to create machines with general intelligence comparable to that of humans. So in 1965, Herbert Simon predicted in his book The Shape of Automation for Men in Management. It's a very 50s to 60s title, The Shape of Automation for Men in Management.
Yes, it is.
And this sounds almost like a counterpart to Norbert Wiener's book.
Yeah, a little cybernetics, information you can, like communication control in the machine and the animal. But
Yeah, Herbert Simon. We should kind of maybe revisit some of his work in the context of cybernetics. He wasn't a cyberneticist, but he did do kind of this management work. So he was in management studies and social science. So there might be some relevance there. Anyways, in this book, he predicted that machines will be capable within 20 years, so 1985, of doing any work that a man could do. And again, this is just kind of, I guess at the time, it's management. It's, of course, not just men, but they're doing things with, they're automating things in offices. They're automating things on the factory floor as well, but I think his focus is office work. So this is, and of course we've automated office work. We've done a lot of that. And, the idea being that you could just automate all of it and that's fine. And of course, in my project management course, I have a whole section on automation and how, you automate something and you can automate things. But what it does is it removes accountability, but it also removes the organizational aspect. So in other words, if you have automation, you spend a lot of time with oversight to make sure it fits into the organization, fits into the organizational scheme, and you end up spending a lot of time doing that as well. We're fixing things that it messes up because it's not well integrated into the organization, into the human capital of the organization. Anyways, so despite this prediction, I don't know if by 1985 that was actually the case. We started to get computers into the workplace, but of course, this has been the vision. In 1970, in Life magazine, Marvin Minsky was quoted as declaring that in from 3 to 8 years, which of course was by 1980, we will have a machine with the general intelligence of an average human being. So, maybe not all of you were alive in 1980, but in 1980 we did not have that. And we don't have that now, we might argue. I mean a machine that will be able to read Shakespeare, grease a car, play office politics, tell a joke, have a fight. So, from a cognitive science standpoint, that's a pretty provocative statement. Because reading Shakespeare, greasing a car, telling a joke, and having a fight are different things. There's procedural memory, there's motor control, there's declarative memory, there's emotion, there are all sorts of cognitive things going on here. And having a machine that does all those things. And maybe that's the lesson here for general intelligence, is that you're talking about different aspects of cognition kind of being able to go between those, just like a human brain does. So we can do procedural memory, we can do episodic memory, we can do declarative memory, we can do motor control, we can do emotional processing, all with the same brain, basically, different parts of the brain. But of course, the idea being is that, you want to have a machine that emulates all of that. And so, that's the idea here of general intelligence. So I heard that there was a comment here in the chat.
Oh, it's a reference to the song, which is this. It's a song, but it's also like this sort of I think it's a great like cultural reference point. It's not that popular, but like it's a song that's about uh the big hopes. Maybe it's like an early wave of AI hope and technology, and it specifically mentions especially about the International Geophysical Year,
Okay.
which is like this like kind of like World Science Fair thing,
Yeah.
but basically like the song talks about like transatlantic tunnels, and like it basically makes references to Star Wars or Star Trek, and how like you gotta get to this like you can just do everything, and we kind of figured out all our problems and stuff like that. Um, it's always funny to look at the history of, oh, it's always 10 to 20 years away. We're having these major breakthroughs, and what does that look like, and so on, and then why or why not those are the case. So yeah, interesting, very interesting, very
Yeah.
interesting set of articles. I like
Yeah.
all those.
So yeah. So I mean, another thing think about is that people have in cognitive science at the same time there was this attempt to sort of understand all these different cognitive functions and how the brain does all these things, simultaneously or with the same basic set of machinery. And one idea, of course, were functional modules. And so there was a whole period of cognitive science where they talked about modularity and strong modularity, weak modularity, and all this. But basically, the idea was that your brain has different modules that do different things, and how did those evolve? How did those function together? And some people think that the idea of modules are bunk. So there's a whole debate in cognitive science, as there usually is about things. But the idea here is that there's this sort of vision of general intelligence. There's the measurement of intelligence and psychology, but also at the same time you have cognitive science kind of trying to unpack the brain from a cognitive standpoint. And then you have this idea of modularity, which of course is and connectionism, which is kind of going on at the same time. So of course, none of this really came to pass. The term AGI was coined in the early 2000s to recapture the original lofty aspirations of AI pioneers, seeking a renewed focus on attempts to study and reproduce intelligence and it as a whole in a domain-independent way. So again, the domains are not important. It's the function that allows you to do things in different domains, but it's all kind of a centralized thing, which of course, again, from a cognitive science standpoint, this is pretty naive because we might have a domain independent thing, but it's not it's tangentially related to some of the things that we're actually when we develop a benchmark and we test it on some performance metric. As an aside, I was going back over the papers on allostasis that we've covered. We talked about the Ellis and Esch paper, for example, on allostasis, and the idea there was that.
Oh, I wasn't sure which paper you're talking about. It's fine.
Oh, yeah. So they're from 2022 is on allostasis. But the idea there is that allostasis is this domain-independent mechanism. And of course, allostasis is sort of how they propose that there's this term allostasis, which is like homeostasis, but it regulates things in different states. And it does this. But this is sort of at a physiological level, and not necessarily like things like emotion, but like a deeper physiological regulation level. So it's optimizing energy flow and things like that, metabolism. And that then regulates cognition. So it's interesting that in AGI, in this concept of AGI, they're thinking about cognition in a domain-independent way. They think, well, there's this domain independence of cognition. There's this master regulation of intelligence. And in this allostasis literature, what they're arguing is that, well, the brain has a domain-independent set of mechanisms, but they're energetic, they're metabolic, and they're regulated through allostasis. And then the regulation of allostasis affects cognition by affecting the conditions under which you learn things, where you can recall things. So, for example, if you're ill, you may not have the kind of memory you would like or the kind of cognition you would like. If you're under emotional duress, you don't have the kind of you can't recall certain details about things. There are all sorts of things that can affect cognition in a way that's not cognitive. So that's a very important thing to remember here, is that when you're talking about general intelligence, you could talk about cognition, you could talk about domain general cognition, or you could be talking about something else that artificial models don't have, like a metabolism or a set of energetic imperatives.
Yes.
Okay. So yeah, then this kind of goes through AGI and kind of what we've learned in this sort of process, and what some of the people in large companies are talking about. And it's still very general. They speak in generalities. So Dennis Hassabis defines AGI as a system that should be able to do pretty much any cognitive tasks that humans can do. So that's not really a definition of general intelligence. That's just saying that if you're a machine, you can do what humans can do. Okay, but that doesn't say how that should be structured or how that should be regulated in the system itself. OpenAI describes it as a highly autonomous system that outperforms humans at most economically valuable work. So we get this economic aspect again, which is where we want to replace humans in tasks. We want to automate offices or whatever, and that doesn't necessarily map to the general the cognitive domain aspect. This is just kind of, if there's a task that we think is repetitive, we can develop a system to do the work, but that's not really modeling intelligence per se. That's just kind of taking those economic parts of it and automating it. So this is, kind of unpacking this idea of general intelligence and intelligence in models and in machines, and talking about super intelligence, and how that's been conceptualized. And, this is such speculative views of AGI and superintelligence by extension differ from views held by people who study biological intelligence, especially human cognition. Whereas cognitive science has no rigorous definition of general intelligence or consensus on the extent to which humans of any type of system can have it, most cognitive scientists would agree that intelligence is not a quantity that can be measured on a single scale and arbitrarily dialed up or down, but rather a complex integration of general and specialized capabilities that are for the most part adaptive in a specific evolutionary niche. So what this means is that you can't say, for example, measure different benchmarks, like if you perform well on spatial cognition tasks, or perform well on memory tasks, or even perform well on like emotional tasks, that those are different things of different types. And so, you might have this underlying regulatory machinery that sort of affects that performance, but the performance itself, they're in different domains, and it's hard to compare them all in the same, at using the same numbers. So you'd have to have different indices for these different things, and then put them together and say, well, my AI performs well in this, but not well in this, and so forth, so on and so forth. But also that human or biological brains evolve in a specific evolutionary niche. So human brains are generally intelligent because they're responding to this need to be very flexible and produce things like culture and adapt to different environments. Whereas, brains in other organisms sometimes are very highly specialized to that environment. Like if you have, like, say, for example, a fruit fly brain, it's very, it's adapted to performing tasks in its environment. It's integrating information in a certain way, and it has specific types of performance for motor control and things like that are specific to its niche, and it's evolved there. And so, we forget about the evolutionary imperative of a brain, how it evolved, how it came to be. So this is one thing that biological intelligence, people study that area, they think about it all the time because it's very important. And usually you're studying within that context. So that's an important point.
Yes.
Many who study biological intelligence are also skeptical that so-called cognitive aspects of intelligence can be separated from its other modes and captured in a disembodied machine. So this is about embodiment and sort of how that plays into this sort of idea of intelligence or domain independent or dependent intelligence. And so, yeah, it's kind of, of course, embodiment gets glossed over in this discussion, and we, of course, talk about that in the lab a lot. So that's another aspect of it. But so I'm going to stop on this for now. And I know Morgan maybe has some things to say.
Well, I was just, just going over those again, and one, like, these are the worst software cases that I've ever heard.
Yeah.
Would we really? These are, they're kind of simplistic, and also. I think Douglas Adams was the first to actually do this right, because when he's talking about deep thought, in terms of like, is the super intelligence going to give us what we actually want?
Yeah.
Because of course it gave us 42, and then it was like, well, did you actually know what the question was? So I think Douglas Adams should be given credit first.
Oh yeah.
At least in terms of thought experiments. Anyway.
Yeah, I mean, this is just kind of like a one person's history of it, but yeah.
Well, yeah, I mean, Bengio was there too, right?
Yeah.
We would ask him to solve climate change and it would wipe us out. Like, I would think we would have a few more software controls on that.
Yeah.
Yeah.
Anyway. Well, anyways, yeah, it's food for thought, and so Jesse had made some points here. Even polyvagal theory is language grounded in emergent properties.
That's why I mentioned that is not in the sense of it's a great theory, but more like it's an interesting interface between sort of the view of, I guess, abstract intelligence or abstract cognitive ability in a sense of disembodied, but abstract also as in just like domain, unspecific, and whatever else. Versus one of the cool things about the polyvagal theory, which is like more like a clinical, therapy thing, and not. I'm not making remarks about the scientific nature of it yet, although there's scientific work there. Is more, it's grounded in depending on I'm not saying this is how the whole field talks about it, but the way I was introduced to it was this explicit sense. It's not about choosing. It's not about being willing. It's about being able. Like, as in, if you are in a specific regulatory state, you do not have options to do certain things. Like, you could say cognitively or emotionally. Like, your regulatory affordances change depending on what state you are in. And I was like, well, that's like, yeah, I think that's a cool. Like, it's nice to see language talking about that from a somewhat different standpoint when we talk about like embodied intelligence and even like to meta brains and other things we talk about. So that was sort of. That came up there, and then so it's and that's like polyvagal theory is 20 years old at best, and very somewhat niche even in sort of that clinical therapy, clinical social work type community. That said, my other point was basically yes, the keep it alive factor. And I think that's one of the most. I would love to write something specifically about that someday, just to talk about it, because I feel like that needs a very clear name and a very clear, like, you have to, like, almost like fundamentals to, I don't want to say embodied intelligence, but just like even like the dev AI theme or whatever, like the sense of understanding, not even in the sense of it's the way that intelligence is, but just differentiating much of the language and literature that's been developed over time hasn't always been aware of or talked about directly in this way of what it means to that biological systems have very different. If you're talking to a biology person, like, oh, obviously, of course, but the people like coming at it from this standpoint of intelligence or general intelligence, you have very mixed, takes on what is that, and what is that? Why does that matter? And like, oh, it should be the same anyway. Or this weird contextual uh,
Yeah.
ambivalence about it at times. And then my last point was basically not just that, which I just previously said, but also like measuring or tracking. The factory of you're standing outside of a building and you know what comes out is like a car, this great thing, but you can't go inside the building. You can listen, you can see, you can kind of peer in, but you can't go in and see how it works. So you're just sort of standing outside of this sort of black box somewhat. But just the difference between measuring and tracking these things in a way that's convenient for human beings to do versus how it works and how things are visualized or measurable from the observer's standpoint. There's all factors that play.
Yeah, so I mean that's important to think about, like this survival imperative, or saying like, we maybe done things in our evolutionary history to keep ourselves alive versus not. So if you've developed certain cognitive abilities, it's to the advantage of the organism. So, but the problem is like when you think about like performance, we don't obviously don't evolve ever improving performance necessarily. We evolve a certain
Right.
type of performance, and then that's within our performance isn't limitless, I guess, is the point. And maybe there are certain reasons for that. There's some evolutionary constraints that come into play. There's a balance of what we want to devote energy to. So like you don't evolve. We evolved a large brain, but it wasn't so large that we evolved it to the exclusion of everything else in our bodies. Basically, the idea. So the way that we kind of think of intelligence, is it like a product of adaptation? Is it a product of constraints in terms of the other parts of our brain? Other cognitive functions. Is it constraints in terms of like allostatic regulation, where we're managing an energy budget and we can only devote certain amounts of energy to different cognitive functions? And then if we translate that into the artificial sphere, first of all, we can develop, I guess, things that exceed human benchmarks. That would maybe give us some sort of superhuman performance on those things. But then could we build a general intelligence which could do other things that would be as superhuman in those other areas? If so, why? And do we want to simulate human intelligence, or do we just kind of want to build things that are like superhuman in nature and just kind of exceed human performance? And so there are a lot of questions there, but characterizing it all as sort of like analogous to biological intelligence is sort of the thing that we want to critique here or think about. Yeah, so this is good. This is good discussion. Any other comments or questions?
Just I'd like to see all those articles, and I'll try to like excerpt some things from them. Or
Yeah.
this is I have visions of trying to basically I don't know how to really, an easy way to say it, which isn't what I actually mean, but like almost like make like a playlist that are topically discussion, like keeping all of the topics of discussion in like one space. And I don't mean like a YouTube playlist. I'm thinking of ways to organize those discussions. So yeah,
we gotta scrape the YouTube pages.
yeah.
We need links.
There's a lot of like cool tools about this now too that I'm looking at.
Oh yeah. Well, I'm pretty sure. What's is it Scrappy or something spacey?
I don't know. Yeah.
So,
Yeah, there are a lot of tools that you can like get, like it'll take the audio content.
yeah, but I mean, we did this off of, because we posted, I think, using Meetup for a long time.
Okay.
And so we had all this like link, basically all this link history on Meetup, and somebody used, I think it's Spacey, SPACY, industrial strength, NLP, old school NLP. But it's just a good way. You can point it at a kind of subdomain, and tell it to grab all the text.
Yeah.
I'll see if you can Spacey for YouTube.
Oh yeah, that would be good. Yeah, Trevor, I see you're there.
Yeah, I feel bad because you talked about it forever ago, but I did have a few words about the ARC challenge because you brought it up.
Okay.
I've looked at this before because I was intrigued by it, and it turns out there's a little bit more than what appears on the surface. So the problem mostly appears to be one of because people have actually written articles of how one would theoretically win the ARC challenge or do much better than anyone's currently done. And the creator has basically created this thing of his mind where there aren't existing tools to really solve the problem. So it basically requires the creation of a domain-specific language that he didn't make, and basically no one has made it. And so once that thing gets created, it would it would permit synthetic data sets to be created, and then the challenge should be solvable very quickly. But it's really more of there's a lot of maintenance stuff and like brushing one's teeth that people don't want to do, and no one wants to spend their time doing. So when I hear the ARC challenge, that's really what I think of. There's basically just a lot of grunt work that nobody has wanted to do. And so I think there's plenty of methods out there that once you had the action space defined, then you should be able to AI that thing to death. So yeah, I just wanted to add that about the ARC challenge.
Oh, okay, yeah.
There was some recent, what was that, like maybe a month ago, Jesse? I think you posted some links. There was some there were some updates on it,
On the challenge?
Yeah, on the ARC challenge. Like
I don't remember.
no?
I believe it. I just don't remember what.
Got it.
Yeah, I remember talking about it too. I don't know what the.
Yeah, but yeah, like I seem to remember there were some people, and Francois Michelet was interviewed, and maybe he was in Demi. Anyway, I'll just have a look while we.
All right, yeah. I mean, my impression of a lot of these challenges is that you can win them by like doing very unconventional sorts of solutions, or like they don't. Yeah, I mean, like the best practices don't always win. It's just kind of like whatever wins, whatever gets you to the finish line. So like I think we were talking about Kaggle somewhere.
Yeah,
and that
was a month.
Yeah,
sorry.
Oh yeah, go ahead. Yeah, that's.
just reposted some new stuff. I mean, again, like he is trying to make it, you know. I mean, he's not saying that there isn't machinery that you can build, but he's trying to make it difficult for current machinery, right?
Oh yeah.
And that is somehow capturing, it's capturing something that we're missing.
Yeah.
Like, would you agree, Trevor? Or like, is it not getting at something valuable?
Well, I do agree that that's what the creator states the intent of this thing is. I don't think that, at least it's not obvious to me that it necessarily encourages new like vistas into like intelligence. I only say that perhaps out of pure ignorance, but I see how this thing could be solved if one took the time to actually create the actions that the creator hasn't defined. And so the trick to me then is, could you come up with something that could then figure out or do what the human's doing in creating those actions? But that doesn't seem to be the emphasis of the creator. But yeah.
So
I put a link to the new videos.
which channel?
Dev AI.
Dev AI.
Yeah.
Okay.
Yeah.
Yeah. So we talked about that when we had that discussion about physical computing. I think last year, where there are different kinds of computers one could build that would be maybe more analogous to the human brain or biological brains that we don't have in the von Neumann architecture of our computers that we have now. So we could build benchmarks for those kinds of machines, or build a machine like that and test and get to something that's maybe more domain general, or maybe there are different things you can do there. But do you need kind of a new architecture? Doesn't exist. And then of course the history of AI has a lot of instances of people inventing languages that are specific to things that characterize semantics, or things that characterize they're not using just out of the box C. They're building these highly specialized languages that do things that are encode a lot of the intelligence. And so it's interesting stuff. Let's see, Dev AI is here. This is the channel. So we have the ARC Prize. This is the YouTube video. And so you didn't have the.
That's just the channel itself. Yeah.
Okay.
It's various things, various small videos.
Okay. Yeah.
That they posted like a month ago. Oh well. Yeah.
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 That's. Oh, here's an article from the New York Times in 1958. Electronic brain teaches itself. So this is back. This is again the sort of making
original
hardware.
Perceptron.
Right. Well, this is the perceptron, but this is kind of like talking about the perceptron in 1958. So the language they use is really interesting. So the Navy last week demonstrated the embryo of an electronic computer named the perceptron, which of course we all know from the sort of classics, but at the time it was brand new, which when completed in about a year is expected to be the first non-living mechanism to perceive, recognize, and identify its surroundings without training or control. So this is this was the vision for the perceptron. Navy officers demonstrating a preliminary form of the device in Washington said they hesitated to call it a machine because it was so much like a human being without life. So this is the Rosenblatt work, Frank Rosenblatt's lab. He conducted the demonstration. The machine, he said, would be the first electronic device to think as the human brain. Like humans, the perceptron would make mistakes at first, but it will grow wiser as it gains experience. So the first perceptron cost about $100,000 in 1958 money, which will have about 1,000 electric association cells receiving electrical impulses from an eye-like scanning device with 400 photocells. So this is much different even from the stuff that we're doing now, and at a much smaller scale, but it was expensive, and it was thought to be sort of an analogy to the entire human brain. So in principle, so they had this section on self-reproduction. In principle, Dr. Rosenblatt said it would be possible to build perceptrons that could reproduce themselves on an assembly line and which would be conscious of their existence. And then, this is the idea that talking about present mechanical brains, it literally teaches itself to recognize objects the first time it encounters them. So again, this is this stuff about where, you're trying to learn things from nothing, from no experience, or from no training. You have not just generalize, but like recognize novel things. So even back then, that's what they were trying to do. So.
Yeah. And Grace Lindsay's book, Models of the Mind, does a great review of that time period.
Yeah.
And the work, the work before that, the work after that. Yeah. I love the embryo of a brain.
Oh yeah. Well. Okay. Well, yeah. So I don't know if we had any more conversation or comments on that before we move on. Now I didn't forget about biological brains, and I've got something here from eLife that is about, we've talked about the fly connectome, and we've talked about some of these small connectomes. So in C. elegans, of course, we have a completely defined connectome, which are these, small nervous systems that have a small enough number of neurons and a small enough number of connections between them that we can characterize them through things like, imaging technologies, and map them and give them names and actually build models that you can visualize them. So this article is, it kind of goes through some of the small connectomes, and then it gets into some of the sort of contemporary work on fruit fly connectomes or Drosophila connectomes. And so this is, I think in a previous meeting, it could have been last year, we talked about Michael Winding et al. And their study on the nerve cord of the Drosophila. So it's basically the nerve cord of Drosophila and this associated neurons. So it's not the entire brain, but it's the nerve cord. And then there's some other studies on other parts of the fly brain, such as the sensory systems and some of the motor systems. And so if you put those connectomes together, you get pretty close to the entire nervous system of a fruit fly, which doesn't sound impressive, but it's actually quite a few neurons. But we do have these smaller connectomes like C. elegans, which is 302 neurons, and some annelids, which have like less than 100 neurons. So this article kind of walks through connectomes, these small connectomes, these complete connectomes that we have, or near complete connectomes, and what those look like. And so one of the things we're trying to do in OpenWorm is to, simulate whole connectomes, very small connectomes, but things that generate behaviors, things that have sensory inputs, and things that produce a sensory motor intelligence. And so this is kind of going through kind of some of these studies that have sort of proposed these connectomes. So, one of the things they do in proposing a connectome is they collect high density imaging data, microscopy or, other types of imaging. And they annotate the images by looking for the neurons, identifying the neurons, usually through some sort of stain, and then looking for the connections. Sometimes they're the electrical connections of gap junctions between cells. Sometimes there are synaptic connections, and looking for those they're able to label those in the images and identify them, and then put together like a database of the cell identities and then the connections, and that's your connectome. So producing connectomes is technically and computationally challenging. Most of the existing ones are of small invertebrates with limited number of neurons. The first generation of connectomes included the nematode C. elegans, which has about 300 neurons, the C-squirt Ciona intestinalis, which is an interesting model organism, and the annelid Platanursis demerili. And so this annelid is the one that has like less than 100 neurons. The C-squirt Ciona intestinalis has a complete connectome, but also has a really nice developmental data set associated with it. And then, of course, C. elegans, and that has 302 neurons. And so the Cook paper and the White paper are the C. elegans connectomes. The White et al. From 1986 was the first connectome for C. elegans. The Cook paper from 2019 provides connectomes for both the male and the hermaphrodite C. elegans. So provides some, there's some differences in the number of neurons and the connectivity there. Versatio, which is, this pops up. This is for the annelid larvae. So this is a whole animal connectome and cell type complement of the 3-segmented annelid larvae. And then Ryan is the one where they have these connectome of the tadpole larva of Ciona intestinalis. So Ciona intestinalis goes through a number of larval stages, and this is the tadpole larva. So some interesting data sets there. But when we get into Drosophila, we have a number of sub-connectomes, you could call them. So Drosophila has a larger scale of neurons, so they have thousands of neurons. So, and we want to be able to characterize every neuron, so we have to take this in parts. And so the first insect connectomes are of the fruit fly Drosophila melanogaster. They include both the brain of both the larva and the adult, as well as a partial reconstruction of the female ventral nerve cord, or VNC. This is analogous to the vertebrate spinal cord that integrates sensory information and coordinates motor output. Now in eLife, Card, Jeffress, Berg, and colleagues report having generated the first full connectome of the ventral nerve cord of an adult male fruit fly. This is Takamura 2024. We haven't talked about this paper, but this is a connectome of the male Drosophila ventral nerve cord. So this, they're making progress in Drosophila and these different parts of the connectome. And really any connectome is any set of connections in a nervous system. So we have connectomes for human brains, but they're largely like based on fMRI. So they're not based on neurons themselves, or based on like regions of interest or voxels. And so, but these connectomes are based on each neuron. So they include, like, for example, this Takamura 2024 includes over 23,000 neurons connected by more than 10 million presynapses, 74 million postsynapses, and a total length of 44 meters of neuronal arbor. So that's a pretty decent sized connectome to look at and have identified at the cellular level. 2 companion studies also to be published in eLife supplement this resource with additional biological insights. So Card and colleagues describe how the pathways linking brain centers to motor neurons are organized, while Jeffress and colleagues cataloged and grouped the neurons in the VNC connectome based on cell type. So these are different ways to look at the connectome, looking at brain centers and the organization of motor neurons, and then looking at the VNC connectome based on cell type, which is, of course, another can of worms that we won't get into, but cell type, basically, they use different markers to determine its function and its typology. So this is something that is useful, especially when you get to that number of cells. What are the specific cell types? And, without really having a good molecular characterization of cell type, what are they doing in the connectome? What's their role? As well as the connectome itself, this group, Takamura et al., which is the paper here, described a robust pipeline built to generate the VNC connectome of a 5-day-old adult male fly. So this is where they have to build this informatics pipeline to like integrate these data and put it into a framework so they can actually extract the connectome. They require combining and adapting state-of-the-art methodologies necessary to prepare and then image the tissue using electron microscopy, as well as the approaches used to align and assemble the resulting images that generate a comprehensive map of the structure. So this is kind of what they're doing. They take the ventral nerve cord, they take focal planes of the ventral nerve cord, they do segmentation of the images, they find the cells, they find the connections here, synaptic connections between this blue cell and this orange cell. You can see that it's present at different focal planes, so they can image different, its sort of position, but its geometry, finding the synapses, and then establishing a connection between the two cells. Then they have this neuronal circuitry that they've worked out. Then they can identify cell types, and that's how they do this. And that's all, that's a lot of work. So, generating these connectomes, they generate this data set that other people can use and find, test different hypotheses, ask different questions of the data. And so, using the resulting data set, Xiang et al. Examined how descending neurons are organized into pathways within the VNC. So they've actually taken this data and looked at the different pathways in the ventral nerve cord. These cells are crucial for movement as they relay information from the brain to the motor neurons that can activate muscles. So computational analyses highlighted 37 distinct neuronal communities that play complementary roles in controlling movements. So this is really getting into the sort of systems level of neural control. So you can do experiments and you can say, you can look at, say, a stain or like some study where you can make general statements about the expression of different genes in different parts of the brain in terms of the structure of the VNC. But now you can map this to specific cells. You know how those cells are connected. You have a very detailed model of how that connectome is operating. So this is, and of course, it's not just about finding sort of the path through the connectome, the distinct cells that are involved, but you have these different aspects of connectivity, such as looping connections, where, there's feedback, and you get this enhancement of the activity of certain cells. So it's not just this path of cells and this additivity. There are these feedback mechanisms that are actually sort of essential to the operation of motor control. So this paper kind of goes on a little bit more about how people can use connectomes and how this is a major advance in our understanding of brains, especially beyond these very small connectomes. And then they talk about comparative connectomics, which is where you can go between organisms. So you can go between like fruit flies and maybe some other insect, maybe like bees, if you had that connectome, and look at differences in behavior, look at differences in structure, and make statements about those. So we had a comment of Flywire AI. That's one of the groups is doing a lot of work with the connectome in Drosophila.
Well, yeah. As I understand it, they're trying to collate all the work of other labs to bring it into to produce something kind of like a resource like Allen Institute.
Yeah. So this
that was yeah.
Oh, go ahead.
Well, that was the first stuff that I saw from. It's led out of Princeton, but like there was this. I think it was a big paper. The PI was from Berkeley.
Okay.
Like showing, doing modeling on that Flywire connectome, simulations on that, and pulling out sort of like I think some olfactory function. It was cool. I think Shu was the first author, like SHIU. Anyway,
Yeah.
it was cool stuff. I mean, this was like the people at the Foresight meeting who, it was suggestive to them that they could recover function solely from connectomics.
Oh wow.
Which I feel is beyond ambitious.
Yeah.
What's the polite way to say so?
Yeah. Well, that's very ambitious.
Unrealistic.
Yeah.
Anyway, it's a great paper though.
Oh, great.
And
I don't know if Trevor had something you want to say.
No, sorry, I did. I was just listening. I just turned my cam on. That's all.
Oh, okay. Yeah, great. Okay, yeah. So that's good stuff. And then I think the last thing we'll end on is these two papers, and this is kind of talking about behavioral stuff, but it's separated from connectomes or from AI, and it's these two papers that are really interesting. And I term this category behavioral freedom, and it's an interesting set of papers that kind of get at this idea, and we'll see what it is here. So this paper is from BioSystems. The paper is called "The Physics of the Urge to Have Freedom." This is kind of an odd title. It's Adrian Bejan. He does a lot of stuff with. He's a mechanical engineer. Has this idea called constructal theory, where he's looking at like different structures and their energetic efficiency. And so this is sounds like a paper where they're talking about free will, but we'll see what he talks about here. So this is an interesting way to kind of summarize behavior from a physics standpoint. The abstract reads: freedom, safety, and ease of movement are innate human urges attributed to conscience, along with many other preferences such as attractiveness, economy, and life. So this is like kind of a way to characterize behavior, but not really linking it to the brain as much, but just kind of this idea of what we do in terms of our behavior. So freedom, safety, and ease of movement. And I think where he's going with this is that there's this imperative to move. There's motility. There's sort of finding a place where you can survive. So the survivability we talked about earlier, and then freedom being not being encumbered. So it's very sort of philosophical terms here. This article addresses the physics basis of the innate urge to have freedom. So it is kind of maybe like free will, but he's going to go from humans then to animals, and sort of, you can think of this in terms of cells as well. So, you have cellular motility, you have animal movement. Those are all kind of, this imperative to move. Of course, we evolved movement maybe in part to escape predation, things like that. So it unveils a connection between animal freedom and the universal constructal, and this is this constructal theory. So the universal tendency towards easier movement and greater access in all evolutionary systems throughout nature, animate and inanimate. The demonstration is made with a model of lack of freedom in animal movement. So this is where he kind of talks about this model, a man who walks his dog on a leash. So this is an interesting sort of model system for this, or toy model. When two animals are coerced to move at the same speed, their combined effort, or the spent power, is greater than when they move freely and independently. So imagine, a human and a dog. A human is walking a dog on a leash. The dog is kind of wandering around. The human is, of course, trying to guide the dog along. And of course, the human can also wander. The idea is that, they're entrained to each other. So there's this lack of freedom and movement. When two animals are coerced to move at the same speed, and I don't know if coercion is the right term, but basically when they're entrained with each other, they're constrained by each other's movement. Their combined effort, or the spent power, so that means like how much energy they're expending on their movement, is greater than when they move freely and independently. So if a dog is moving independently, they're spending less energy than when they're entrained to a human, and vice versa. When the speed of the couple is dictated by the big body or the person, the big one walks freely, the small one must run. So this is where, you have human walking maybe faster than the dog, and there's this like an anatomical constraint to movement. So when I take a stride, if the dog is smaller than me, they have to run to catch up. Now we have big dogs in this house, so this is maybe not a good analogy, but whatever. Let's just assume a very small dog here relative to the human stride. Participants in organized movement, life, and society are not equal. All participants move with less effort when they are not coerced to move the same way. So the implications of this part of physics or nature are numerous and help unify the animal realm with the design of an evolution of human society. So this is kind of getting into this sort of constructal theory. The reason I like this paper, or I wanted to highlight it, is because it's really kind of talking about the physics of movement and thinking about like those kind of relationships and how that guides behavior and how that guides some other things. So think about this in terms of the physics and in terms of like complex systems and movement and how that movement is being generated. And they don't talk about a brain here, but of course the nervous system is generating this. It's actually kind of interesting. This model of the human is walking a dog on a leash reminds me kind of some of the things that they're doing with synergetics, especially some of the stuff that J.S. Kelso has done with synergetics, looking at different coupled systems. And we've talked about J.S. Kelso synergetics in the Cognition Futures group. I think I gave a short presentation on it there once, like a year or so ago. And so they're looking at these kind of coupled systems in trained systems. And so this also talks about, sort of the output of muscles, which are controlled by energetics in the brain, and sort of the constraints on those kind of systems. So, he talks about the physics here, talks about some of these aspects of, this is a theoretical paper, and then getting into sort of this philosophy of human nature, urges, and some other things here. So it's an interesting paper, but hold that aside for now. And the other paper has to do with something called aggregate Boyd behavior. So if you're not familiar with Boyds are sort of simulations of birds. And so the original Boyd's platform was where you have a bunch of computational agents, and they're put into an environment, and they all exhibit these collective behaviors. Each Boyd has a set of rules that it follows, and a set of neighbors, and you have this, this parallel set of behaviors by this parallel set of agents, and they behave like. And it turns out that they can replicate the behavior of bird flocks just by having these individual Boyd agents all following the same set of rules. And then in just interacting with their neighbors and having this parallel system of agents that are like, basically behaving in concert. So that's what they mean by aggregate Boyd behavior. And so this is where you can simulate, collective behaviors just by simulating the physics of interaction. Don't get too close to your neighbor. Don't get too far apart from your neighbor. Match the speed of your neighbor, and so forth. So there's this the set of physics that govern these relationships between agents. In the first case, it was the person and the dog being coupled by a leash. In this case, it's these Boyd agents being coupled by rules that say, here are the conditions of your interactions. Now, this aggregate Boyd behavior aids in artificial autopoietic organization. So autopoietic organization is a type of complex systems view called autopoiesis, where you basically it's trying to model this sort of lifelike behavior, this lifelike regulation of systems. And so they get into this idea of Boyd's, and they kind of get into some of these. So this is also from BioSystems. So they kind of think about this same problem, but recast in terms of autopoiesis. So I won't start at the beginning of the abstract. I'll start down here, where it's a systems level characterization that is and referred to as a general pattern of minimal life is autopoiesis. So this is defining sort of this minimal type of life and the kinds of conditions you need to regulate that. So they're using this framework of autopoiesis, and in the previous paper they used something called constructal theory. So they're using different kind of theoretical bases for this same set of interactions. But autopoiesis basically describes a living system and describes the minimum conditions for that. So autopoiesis includes production, maintenance, and replacement of required parts for setting up and maintaining an internal environment with self or other separation. And there are a lot of words here, but basically it's how do you maintain a living system, or maybe better yet is how do you maintain a self-contained dynamical system that doesn't need any external input. So this is where they use autopoiesis. The seminal concept of an autopoiesis is instantiated in life as we know it, but might also be instantiated in different media. So this is when they get into these Boyd simulations. So other researchers have argued life is more than autopoiesis, and that it is a co-emergent property of autopoiesis and cognition. So this is where we get into these Boyd simulations, where you have these physical interactions of agents, and you can describe it as autopoietic. You can also describe it as this sort of constructal theory, which is looking at the structural aspects of a system and looking at its energy minimization. Or you can look at it as a form of cognition, where you have cognitive functions or intelligence that's maintaining these relationships. Life produces many emergent properties, such as a synchronization and patterns as seen in flocks and herds. So you see this in a number of animal species where they form these behavioral collectives, flocks, herds, schools, and they're just basically organisms interacting with each other, following simple rules. Maybe follow my neighbor, or don't get too close to my neighbor, or don't get too far away from my neighbor. And when you have that happening in parallel, you get these structures that are, large-scale collective emergent structures, such as flocks or herds or schools. And so that's the description of these structures. But it's something that isn't, kind of put together by a master plan. It's something that just emerges from interactions. The mechanics of the synchrony displayed in flocks and herd animals has been extracted by Craig Reynolds. So Craig Reynolds was the computer scientist who originally ran these Boyd simulations. And this is, of course, considered a generative model because it generates a lot of different solutions for a simple set of interactions. So when you run the simulation over and over again, you can get different types of configurations of these types of collective systems, but they are all basically the same type of thing. With these concepts in mind, we address the following research question. How can the synchronous maneuvers and aggregate behavior of Boyd's contribute to the constitutive subsystems in realizing an autopoietic system? Can such a system exhibit minimal cognition? And so they get into this whole attribute of autopoiesis as an explanatory framework for these collective behavioral structures, and thinking about this in terms of minimal cognition and the intelligence of these types of structures. So this is, we have two papers here. We have one that's sort of claiming that if we look at these kind of simple systems that are basically behavioral systems with physical constraints, we can get, we have this sort of larger scale set of structures that emerge. They can be explained using these types of universal theories. And in this case, it's constructal theory. So you can see that there are a lot of equations in this paper where they kind of model the physics of this interaction, of the walking interaction, the coupling of the two agents, and really gets into a high amount of mathematical detail here, where there's like these kind of parsing out the effects of the efforts of both agents and how those are coupled and how they're efficient energetically. And then we have this other paper where they're looking at these Boyd systems, where it's again a collective, where they're coupled agents. And he's using a different theoretical framework, namely autopoiesis, which is this, the sort of emergent properties thing that describes sort of a self-contained system that doesn't need external inputs. So this is something that, again, describes these kind of structures that we see in nature, and you can simulate them. There are these physical constraints between the agents, and it's a different explanatory framework. I don't think there's a lot of mathematics in here. They're different like conceptual models. And you have some mathematics in here. Kind of describes some of the aspects of the collective structures, such as velocity changes and cohesion. There are parameters you can measure in these as well, but it's not as mathematically voluminous. But this is another theory. So I want to just go over those. I think that's I just wanted to see if I could actually sort of stitch those two papers together. But I think it has a lot of things to do with sort of the physics of behavior and intelligence and that sort of thing.
Certainly coming off of this year's A-Life meeting, like those are certainly the Boyds would be very in the theme. And he's got a GitHub link there and YouTube video of some animations in terms of the second paper.
Okay.
Take care, Jesse. So the first paper seems to have a real focus on synonyms.
Yeah, I know.
and how these discussions change when you use different words.
Right. Yeah.
There's a lot of emotional content that comes with those words.
Yeah.
Potentially, but the math seems to be very focused on, like you said, stuff you see in planetary dynamics as well as other physics, other physics work, and I mean it. So I'm not sure what we didn't quite go through the paper. So in the first paper, I don't know what his kind of objective was at the end in terms of demonstrating. I think you used the word efficiency.
Yeah.
There was an efficiency to the kind of relationship between the two bodies.
Yeah. So there's this whole aspect of like energetic efficiency, and like a lot of times we'll describe physical systems in terms of like minimizing entropy or being maximally efficient. So that's what basically constructal theory is about. And so, you have this behavioral system where you're minimizing sort of, maximizing your energetic efficiency. And then that leads to like these behaviors that are, so,
Yeah, sure.
And
there was something that you were talking about earlier. I think in terms of the economics of behavior, that it reminded me of one that one of the talks Levin had this week. One of the talks he posted on his, Levin's, what is it called, like academic content YouTube channel.
Yeah.
Which I think is just a funny name. He had somebody focused on that. I think an economist. He had an economist talking about how their work can be considered as part of his what is it TAME
TAME framework,
minds everywhere. I forget what the TA
technological something.
Yeah. But also, it kind of reminded me of what was the kind of robotics animal behavior book in the mid '90s from like McFarland and.
Oh yeah, I know what you mean.
It's like, yeah.
We've talked about this before, but I can't remember the name.
Yeah. But they also talked, about how economics kind of comes into planning and behavior.
Yes.
Yeah.
And there's a whole field called psychonomics where they do this sort of thing.
Oh, really?
Yeah, there's a psychonomic society, and they kind of like the basis for cognitive science. Like a lot of connection between cognitive science and like these kind of I guess you could think of it as maximal efficiency models. That sort of thing.
Is it similar, or certainly I think of it as like that, so much wouldn't work without like inductive biases and things like that.
Right.
And those are can one way of seeing those is just kind of like as an efficiency mechanism, or certainly as a this is how you deal with the huge amount of data and the kind of drawing the inferences from them to be actionable. Okay, so was that a similar time frame? Was that like late 50s, 60s?
Well, I think a lot of that, was coming out of that period, but I don't know. Like, I think, like there was a lot of stuff, I think the whole basis of cognitive science really kind of came out of, or at least one of the aims of cognitive science was to, replicate what they saw in economics, which was you could have this highly predictable social science. You could use mathematics to characterize it. You could get like, and then there's a lot of other work in cognitive science that kind of maps to economics, or there's overlap. So that's really interesting.
Sure. Are you talking about like the Cannon kind of stuff, or
Cannon,
just kind of like broad macroeconomic theory?
Oh,
well, Kahneman was doing like all this. I would call it behavioral psychology, but with eye tracking, or he was doing that kind of pupillometry, right?
Yeah.
So he was giving people cognitive tasks, and then using the pupillometry to show workloads levels and kind of breaking points of people in terms of when cognition was going wrong, but it helped reflect what the mechanisms were.
Oh yeah, well yeah, I think that's what they kind of mean by psychonomics, that kind of work.
Okay.
Yeah, it's just using like models. Yeah.
Okay. How do you spell that word? Yeah.
Oh, what was that?
How do you spell that word? If you could put it into.
Oh yeah, psycho. It's like psycho and then nomics, like that. Yeah, there you go. Yeah, it's just portmanteau of psychology and economics, I guess. Yeah.
Okay.
But yeah, it's
I'd never thought about the etymology, I guess.
Yeah. It's an approach. And then of course, you have physics, which is the physics of behavior, which is like just saying that behavior conforms to physical laws. You can use, that there's universality, and this is something in complexity theory, which is the assumption that you can use, things like power laws and network theory to describe any range of systems, and they don't have to be like specific to like any brain. They can be like humans, animals, power grids, whatever, and they all follow basically the same laws because when things interact, there are certain things that happen, certain constraints, and then those kind of apply universally. So I mean, that's that's an assumption. I don't know. Some people have said that's
certainly
simplistic.
that's very that's very Michael Levin too, right?
Yeah.
I mean, in terms of you can find these things, and Josh Bongard had I forget I don't think it was his work, but it was like maybe one of his students again for A Life had physical systems that were learning systems.
Oh yeah, I saw some of that. Like it was like chemical. They have like chemical systems that are like they use them to model emergent intelligence or something. I have to go back and get that paper out.
In this case, it was mechanical.
Okay, mechanical.
Or it seemed again it was kind of like mass action.
Right. Kinetics.
Yeah. But with locality.
Okay.
Yeah. And I'll try and drop the video in. I put the video that the Boyd's guy had in Brainbird vehicles.
Okay.
Yeah. But the other thing that came to mind, it's not directly related to flocking, but just this guy Edwin de Jammer in Bristol had an interesting paper just about birds. What do you call it? Birds migration. Yeah.
Okay.
So a really simple mechanism, and was and like again, this is a guy who I know from I think Pi. What's he doing this? He's got a Pi eye tracking software package.
Okay.
He's an experimental psychologist, right?
Yeah,
But he did this paper. I think it was during the pandemic, and he first published it in an archive as just like, I came up with this because I'm trapped at home. But I just saw it got published in some birds or ethology.
Ornithology.
But again, just similar though in the sense of like using some very simple physical mechanism and getting out these behaviors that seemed intelligent, right? And efficient. That was I think the other thing that was important in terms of the problem that the birds were solving.
Yeah.
That was I'll find that guy too. But anyway, I know it's
Yeah.
I know it's 9:30 here.
Okay.
I also see people behind me.
Right. So Trevor, did you have anything to add or?
I mean, I'm sure you immediately see the connection as well. But in the first paper, it reminded me very much of Carl Friston's ideas about like life and movement. So
Sure. So
that's about all I got.
Free energy principle, active inference kind of stuff.
Yeah, exactly.
Yeah. No, good point.
Yeah, we'll probably revisit this. I like I said, I just kind of put together something I want to see how that was, what we could get out of it. But we might revisit this later. So, especially maybe free energy principle type things.
But you should definitely do or see if anybody else did a kind of recap of A Life 2024.
Oh yeah,
and,
maybe.
In terms of just and was Gecko overlapping with that?
Yeah.
So just see highlights from it maybe. Certainly, I saw people dropping videos and
Oh
things
yeah.
like that. Yeah.
Good stuff. Okay, well, thanks for attending, and we'll keep in touch in Slack, and see you next week.
Take care.
Take care. Thanks.